Okay, we're going to review the Newton's Laws review sheet. I'm just going to talk through these answers quickly. You can skim through if you want just to get the answers, or you can follow along. It says, number one, a car is pushed to the gas station with a net force of 5,000 newtons. If it accelerates at a rate of 15 meters per second squared, what is the mass of the car? So we have the net force of 500, an acceleration of 15, and we're looking for the mass. Well, this one is pretty simple, gives us everything we need. Mass is the net force divided by acceleration, 500 divided by 15, 33.3 kilograms. Number two says a 2.1 kilogram soccer ball is struck with a 45 Newton force, which is applied for 0.3 seconds. What is the velocity of the ball after it was kicked? So really what we're looking for is the final velocity after the ball was accelerated. It's going to be accelerated for 0.3 seconds with a force of 45 newtons. So we're really looking for VF. Once you know we're looking for VF, that makes things a lot easier because we know the initial velocity then is 0 because the ball wasn't moving before it got kicked. The mass is 2.1 kilograms. The force, since it doesn't describe any frictional forces or any opposing forces, that 45 Newton force is the net force, and then the time is 0.3. So eventually we're going to get down here to this VF equation looking for final velocity. There's only two options really for final velocity. The VF squared equals VI squared plus 2AD, or VF equals VI plus AT. And so we're going to use this one, VF equals VI plus AT. So we have the VI, we have the time already, but we need the acceleration. So that's how we went up here and did A equals Fn over m, 45 newtons divided by 2.1 kilograms, and now we have an acceleration of 21.4 meters per second squared. We can fill that right in here, and then we have a final velocity of 6.42 meters per second. Number three, what is the mass of a car that is accelerated to 15 meters per second after being pushed by a 510 Newton force? And it was pushed for 12 seconds. So we want to know the mass. We have a final velocity of 15 meters per second. It doesn't say it on here, but I think on your sheet it even says that the car was at rest. It should say that the car is at rest when it starts. And so we know the VI is 0, and it has a VF of 15. The time is 12 seconds. So same type of problem, just a different variation. In order to find the mass, we need a net force and an acceleration. We don't have the acceleration yet, so we have to go VF minus VI over T, which is 15 minus 0 divided by 12. That's 1.25 meters per second squared. We can fill that in below, and we're going to get 408 kilograms. All right, number four. Not all of number four is fitting on my screen, but we'll scroll down for you. It says a car is traveling 15 meters per second and slams on the brakes because of the car in front of it suddenly stopped. It took 1.2 seconds to stop. The car is a mass of 3,500 kilograms. How much force was needed? Initial velocity is 15. Final velocity is 0 because it's stopping. So this one's a little bit different. We have a time of 1.2, a mass of 3,500 kilograms, and a net force of a question mark because that's what they want us to find. So to find the net force, we got to go down here and we have to say mass times acceleration. We have the mass of 3,500 kilograms. We don't have an acceleration yet, so we had to do this equation first. A equals VF minus VI over T, 0 minus 15 over 1.2, and you get a negative 12.5 meters per second squared. That negative is key. That indicates that the car is slowing down, it's stopping. So you have a negative acceleration. That's perfectly fine. That's exactly what we want. Then we can put that negative 12.5 meters per second squared here, and we end up with a negative force of 43,750 newtons. And again, the acceleration was negative, so the net force is negative. It's a stopping force, and that's fine. All right, on the back side, we just have these. I'm not going to go through all of them, but action, reaction, force pairs, you just turn the wording around. You don't want to do cause and effect, where you would say what the outcome is going to be. You just list the two forces. So the first one says the force of a bat on a ball. The reaction force would be the force of the ball back on the bat, equal and opposite. The force of a foot pushing on the ground, the force of the ground pushing on the foot, those would be equal and opposite. You can see the rest of them there as well. All right, 6, mass is inertia, right? Mass is inertia. The amount of inertia an object has is directly related to the mass. It doesn't have to do with the velocity or any other factor other than mass. Newton's first law, an object's tendency to resist a change in motion, that's the law of inertia. We know that an object will not change its motion on itself unless there's a net force on the object. As soon as there's a net force on the object, it's going to accelerate in the direction of the net force. Until then, it's going to keep on doing whatever it's doing, whether that's at rest, it's going to stay at rest, or whether that's in motion, it's going to stay in motion. 8 and 9, this is Newton's second law, the relationship between force and acceleration, they're directly proportional. If the force goes up, the acceleration goes up. If the force goes down, the acceleration goes down. If the force is doubled, the acceleration is doubled. If the force is cut in half, the acceleration is cut in half. It's a direct relationship. Number 9 says, explain the relationship between mass and acceleration. They're inversely proportional. They're inversely proportional. So in this case, if mass goes up, acceleration goes down. If acceleration goes up, mass goes down. They're inversely related. Number 10, I can't get it on my screen actually, sorry, but number 10 just talks about Newton's third law. For every action force, there's an equal and opposite reaction force, and we explained those force pairs above. All right, hope this helps. Thanks, guys.